or so versus the 30 to 60-second drift from the Super Bowl. We've built a network to scale to really large audiences. Encourage everyone to meet the Phenix engineers here who built it. I had nothing to do with building it. I just try to sell it. And we've deployed that over 34 points of presence across the globe. So it's like a real-time CDN. And the purpose of the talk today is to talk about how to do server-side ad insertion within that context, which is significantly more challenging than standard workflows. But we've now launched that, and that's kind of the focus. So a lot of people say, well, why does real-time matter? Why should we care? The answer is really about interactivity and whether or not it's a fully lean back experience, which the reality is younger audiences today are looking at least 2 screens, maybe 3. They're playing fantasy, they're betting on sports, they're talking to their friends, they're in a video chat. And so the lean back experience, we believe is in the past, and the future is about how consumers interact with content. We work with a lot of big customers today. I don't need to stay on this slide, but across a number of industries, the early adopters of real-time were auction platforms where you have to be enabling users online to compete with those in person, so you have to be super fast. But now we work across sports, betting, iGaming, and general media and entertainment use cases. We've done a lot of big events. We did the Super Bowl a couple years ago in partnership with Verizon. We've done the Indy 500. This is actually our biggest week of the year. We have Cheltenham on here. It's essentially the Kentucky Derby of Europe. It's 4 days, 7 races a day. And I think our peak audience this year was around 430,000 peak concurrents. So larger audiences, not quite Super Bowl size audiences, but it's been a very fun week for us to have these size audiences on the platform. We try to make it really simple for customers to get content into Phenix. So we're flexible on the ingest side. We have our own encoding software, but also a lot of companies already use dozens of different encoder vendors. So we can take in standard protocols like RTMP, SRT, Zixi, or the new WebRTC ingest protocol called WIP. So we support all those standard inputs. This is an example of the F1 event we did with Verizon a few years ago, where we actually did client-side ad insertion. We've been doing client-side ad insertion now for several years, but doing it server-side has a number of benefits to it. And now we can enable these use cases with server-side ad insertion workflows. And it enables customers to make a switch from high latency workflows to real-time workflows without replacing their ad vendors, their ad servers, their decisioning engines. So we want to comply with as many standards as we can in the ecosystem to enable customers to launch things like this. We won't read the list of features off the page, but generally we've built a feature set that is standard compliant. It looks a lot like what you do in an HLS or MPEG-Dash world for doing server-side ad insertion, but the underlying protocol here is WebRTC and requires us to stitch the content a lot faster and do some fancy things under the hood that Tim and our team can tell you more about later. But we have so far partnered with Magnite SpringServe and Google Ad Manager as the first 2 ad partners that we've integrated with. So customers that run on those ad networks can seamlessly work with the solution. And over time, I'm sure we'll expand that group as customers look to use other ad platforms as well. Generally, how does it work at a high level without going into too much technical detail? As I said, we work with a number of encoder partners. Videon is one of those platforms that has a very nice cloud management portal for managing contribution streams. We can take in SRT from a Videon box anywhere in the world, ingest that into our cloud platform to the nearest point of presence. The SRT stream already has the SCUDdy35 markers. Some companies are going to insert those markers in their production workflow. Others are going to use cloud functionality from companies like Videon, where you can actually, via API, insert SCUDdy markers into the stream at the encoder level, which is something that our customers are interested in doing. And then we have to act on that SCUDdy marker. We reach out to the ad asset storage to pull the proper ad content into our network. we're talking again to either Google Ad Manager or SpringServe via VAST. We pull that content in, we transcode it to multiple bit rates to match the ABR strategy for the underlying content. And then we send the ad beacons out to the beaconing server to provide all of the feedback data that a customer is going to expect from ad insertion to understand, how long content was viewed and all of that, the underlying data. And then ultimately, we're delivering our own version of WebRTC, which we call Phenix Interactive Transport Protocol, but it's Phenix's implementation of WebRTC down to clients that are viewing it. So this is kind of the high level what it is. I'll pull up a demo just to show you how that works in action. And of course, hopefully that live demo works as we think it will. So no pressure, but you can see here, these are 2 streams that are being contributed from our San Diego lab from an encoder sitting there. They're being played back with WebRTC over our network. I'm just on Wi-Fi on my laptop here, subscribed to them. I think each of these streams are at about 1.6 megabits per second, so they're not super high bitrate streams. We have the ability to do 1080p at higher bit rates. And what happens when we click the Insert Ad button, essentially it immediately inserts a SCUDdy marker at the encoder. It's an immediate marker. We ingest the stream over SRT. We read out the marker. We reach out to, I believe this is tied to SpringServe, pull in the ad assets, and that can be multiple different ads that are personalized based on where viewers are or what business logic is in the ad system. So we're not making those decisions, but we're acting on all of them and inserting them into the stream. On the left side is a full replacement, and on the right side is a squeeze back to show a different experience. So if I do it on 1 and we go 3, 2, 1, we click, you get 2 different ads delivered, and actually that's supposed to show the underlying content. So I think we have a bug in this part of the demo because that should be the underlying stream of the game, but it's actually showing the ad right now. But what we're showing is 2 different viewers getting 2 different ad experiences. And from the time we clicked the button until the time the ad showed up from the marker was give or take 600 milliseconds. And that's from the time all the way reaching out to the encoder, inserting the marker, reading the SRT stream, reaching out to the ad server, transcoding the asset, inserting it, and delivering it down to the viewer. So all done super fast for customers that are looking to build interactive video experiences. So that's it in action. Apologies for the duplicate ad on the right side. And we built the squeeze back with another partner called Singular Live. That's a live graphics company that built some really cool stuff. So that's the demo, and I'll hand it off to Tim if I can find our slides to maybe share a little bit more detail about how we built it and some of the challenges we've had.
Yeah. So as Kyle mentioned, the first thing is making sure that we can maintain our low latency, which means that we have to do our best to get the signal in. You mentioned that we're using SRT, so customers are going to be interested in protecting the content throughout the pipeline, so they're going to use a secure transport to do that. That of course we have to get that decrypted internally, so we're bringing that system in. When we get it into the encoder, we will turn it into an ABR stream. Right, so we can, at that point, we get that multi-bit rate signal passing through. And when we get into the network now, we have all those different layers that we have to be able to encode. So when we finally get to the ad insertion, right, we have to think about the fact that we have to get out and get the content. We've got to, it's going to be personalized content, right? We're using the demographics from every subscriber because you got the subscribers coming in here telling us who they are. That ad is going to be a personalized ad. We're getting those demographics up into the VAST network. We get some responses. We get a manifest of ads. We have to pull those ads down. We've got to encode those ads to be able to insert into our streams. And the result, as you saw, is we get that in a very low transition time. I'll share that one of the ways we can do that is we have to maybe seed some ads, right? So we're not waiting around for that first ad marker. When we know who that customer is, we've got some idea here. We maybe prefetch a first ad or something like that. So that buys us a little bit of time, right? So as Cal mentioned, the ad will play out, and then we're getting the reports back so that we can report back up into the, with the tracking for the ad plays, right? So yeah, end to end, it's very fast. Again, talk to some of these engineers that are here that made this thing. It's amazing to think that we can, and this network that we have at scale, be able to feed so many streams to so many viewers and still insert independent ads for each one of them. Right? But we do it.
Thanks, Tim. And the only thing I'll add, which is it's fun to be part of a company like this, because when the company was started, everyone said WebRTC was used for video conferencing. It's not used for broadcast. The quality is not good enough. You have audio video out of sync. You have end users with poor connections, and you're going to get lots of freezes. And it just can't be done at scale with hundreds of thousands, let alone millions of viewers. And then we started to prove that out. And then the next step was, okay, if you want to get into broadcast use cases, now you need to do server-side ad insertion. And most of the market said, well, in a WebRTC context, that's not possible. It's not, you don't have enough time to even do the prefetching and all the things that you have to do behind the scenes. So it's exciting. This has been a multi-year effort to get this into production and starting to roll it out to customers. So anyways, that's the presentation. If anyone has questions, either online or here, feel free to ask.
Good. I'll go first. So for the Phenix encoder, it does say like it's flexible on the ingest side. Are people able to use their already existing encoders to maybe kind of insert into that process, or do they have to use the Phenix encoder?
So the Phenix encoder ultimately will still run in the cloud. So you could use a third-party encoder, Haivision, Elemental, Videon, Teradek, you name the encoder, we support most of them. And stream might come in over SRT, and then we go through a transcoding process to create our own bitrate ladder in WebRTC. So we're changing the protocol and potentially the output bit rates of the incoming signal, but it doesn't require someone to like change their on-prem hardware if they have a rack of Elemental encoders, for example, and they want to use those for the initial contribution. So our encoder can sit on site on off-the-shelf hardware, and that can be the source. Instead of doing SRT, we do WebRTC the whole way through. But more often than not, a customer already has their existing setup and they want to minimize how much they have to change in the workflow. Had any questions online? Okay.
You were showing the singular ads with the banners. So are you re-encoding the original content plus the banner and the ad, or are you like just doing an overlay on the client side? How does it work for that particular format?
I believe that one is done client side, that demo that we showed through Singular, which enables you to do a lot of creative things in the UI. But there's a lot of different ways that we've contemplated this with customers that they can accomplish it. And we essentially can draw the video element wherever they want on the screen and show essentially two streams at once. So you can show the ad content in one part and the stream in the other. But I believe what we showed today was done client side.
Okay. Is there a server side approach? Because I know the main reason some people go to SSAI is, so for some TVs, they only want one play ad at once.
So for the full replacement, absolutely. I think on the L-bar, there's some other things to think about in order to make that work across all the CTV platforms, like you mentioned, because a lot of them don't want to enable you to play back multiple streams at once on the screen. So oftentimes, like if you have multi-view on mobile or on web, you can have multiple independent channels playing back, but on a CTV device, you might have to have one. So depending on the device, there might have to be different strategies. Pat?
We've got a
online
question from Mike online. Does Phenix use simulcast for bitrate adaptation on the distribution side?
I'll give the short answer and maybe Tim can give the long answer. The short answer is no. We built our own proprietary multi-bitrate transcoding capability. So we can ingest the, high res MES and then create the full bitrate ladder according to kind of our standard ladder. And that's our own process that we built that runs in the cloud. A lot of other WebRTC companies do use simulcast. And there's a few advantages that we think to doing it the way that we do. The decisioning is made server side, so the client is constantly sending back the information to the server, but ultimately the decisioning of switching bit rates and sending a different stream down to the client is done by the server, which enables the client to maintain more consistent playback. We also built a dynamic keyframe generator that enables us to do switching very quickly. If you're looking in a standard HLS world and you've got 2-second GOPs, you got to wait for the next GOP to get a keyframe to switch your bit rate. But in our stack, we're able to insert those kind of immediately and put you on a temporary layer before we shift you to the official layer at the end of that group of pictures. So there's a lot of creative things we've had to build to try to enable a true broadcast experience and make it less like a video chat. Tim?
Yeah. Well, you covered it. It's we have patents in this area that allow us to use our technology that way, and yeah, we're not sending multiple streams. We're sending basically a single bit rate at a time, right? If you will, sequence.
So at the beginning, you mentioned that you decrypt the content. So what kind of decryption is that?
Well, it's coming in typically over SRT if it's that protected content.
Yeah.
Yeah. So that's everything's agreed upon with the customer there. They're sending us a SRT signal. We have the ability to decrypt that.
Is there a DRM encryption as well used?
Not on that signal. No.
But the next generation of this slide is Phenix SSAI and DRM, which we're very close to having rollout of. We didn't include it in this presentation, but that's kind of next up for us in terms of delivering a true broadcast feature set. So that's coming soon.
So are you in final stages or still in the process of developing?
Getting close.
Yeah, we're better than 50% of the way there. And it works. I don't know if we might be able to demonstrate something, but yeah.
Well, thanks everyone. Take a 2-minute transition for the next presentation and get it pulled up. Pat, if you just want to just mute us for a minute.
Sounds good. Rebecca, send clapping emoji.
We'll see.
Okay. So I'm going to talk about multicast EBR today. just talking about the technology by itself, and then giving you some feedback of what we have been deploying on the field. So I did that with PowerPoint, so you will not see my great animation, but just a few words about me. So I'm French originally, you may have noticed with my accent. So that used to be me, like in the past. Now what you don't see in the back is actually, let's see if I can, no, I cannot show. It's all of my pictures, like watching the Pacers, watching like IU, and watching the Fuel, actually. So I'm a user by adoption since 5 years now. Working in the streaming industry for more than 10 years, building a NAS, SaaS at Broadpeak. If you feel that you don't understand me, it's not you, it's me. Even my mother-in-law have like a lot of issues with my accent, so I'm still working on it. But so I'll try my best tonight, and I'll let you read about my opinion about the Pacers. But if Ben is like in good health for the playoff, I'm sure we can go very, very far this year. All right, so let's talk about like what is multicast ABR. So just a quick story. In 2022, I don't know if you're familiar with DAZN, but DAZN is a big sports streaming service. They acquired the right for the Premier League in Italy. And Italy used to watch a lot of soccer through satellite. The broadband network in Italy were not super developed at that time. It's crazy to think about that, but it was not. And so from one season to the other, DAZN took over in August 2022, and they stream everything from internet. Of course, like not by satellite anymore. Everything from internet. DAZN is an OTT service, and the month of August was a disaster. It was not a disaster because of DAZN. It was a disaster because of the ISPs in Italy. They don't have the network capacity to actually deal with all the stream coming from internet. So they got a lot of issues in the core network. They got a lot of issues in the last mile. Because again, like there were not a lot of fiber. The cable network was not very good. And it was a disaster in August 2022. So people were like that. In Italy, soccer is super, super important. It's like a religion. So people were crazy. They were almost like striking. If you see that the government called DAZN and say like, guys, you need to get your shit together because people are going to strike and it's going to be a disaster. So what happened is like they called us in 2022 during the month of August, and they look at implementing multicast ABR, which was on the way for them to deal with the surge of stream coming from internet. And it was a technology used by some ISPs in Italy to deal with that. Again, you will not see my great animation, but behind that you will see that like Italians are super happy now, and they enjoy soccer after that. So what is multicast ABR? So first of all, multicast ABR, it's while it's used in the streaming context, video streaming context, it's really a technology for network. Okay, and it's very useful for live events. The problem we see with live events, and you probably see that as well, is when you dimension a network, you typically dimension a network for 95% of the time. The problem is like, maybe once or twice a year, you have like this peak of traffic coming from live sports or for like unexpected events, elections or I don't know, like or the Olympics, and you typically need to increase the capacity of your network just for that couple of hours. So, if you look at investment, that's not really a good investment, right? Like you invest for 2 hours, but the rest of the time, you don't really need that capacity, right? So multicast ABR is actually helping with that. How does it work? So multicast ABR, the technology itself is mainly composed with two main components. One that we call the transcaster, and one that we call the receiver. So if you look at DAZN or whatever like OTT service, you probably know that very well. You have encoders, packagers. They use CDN to do the distribution of HTTP adaptive bitrate streaming, so HLS and Dash. And the way that it works is like in the ISP network, in a managed network which can support multicast, you deploy that server called transcaster, which is able to pull the live event in HLS or in Dash, and it's transforming that HLS and that Dash into a multicast ABR. So what it does is basically it's taking over the HTTP header, and you replace that by your UDP header. So
the main consequence is like, well, now that we have like a multicast in the operator network, you don't really need to deal with the number of like concurrent stream. For one event, you have one multicast stream. It doesn't matter if you have 10,000 subs watching or if you have 1 million. It's only one stream in the network, right? The way that it works is like when we create the multicast ABR feed here, we use a transport protocol. So there's, depending on the norms and depending on the standards, you have different options, but you do that in the network. And in the home, typically on your Wi-Fi router, or sometimes on the set-top box, you have a small agent, a small piece of software, which is able to actually subscribe to that multicast and reverse back to HLS or to Dash. So it's actually doing like the opposite. Is removing the UDP header, it's moving back to HTTP header. So from the player perspective, it's actually HLS and Dash the same way that is coming from internet. The player itself, it doesn't even know that multicast has been used in the network. So in terms of encryption, DRM, all of that stays the same. The bit rates, all of that stays the same. The player doesn't even know about it. Okay? So now you are going to tell me, oh, Mathias, multicast, there's so many errors, like there's no acknowledgement, so there's a lot of errors. Well, that's the good thing about that is like we still can, use HTTP. We still use, you can still use like what's coming from internet. So when there's like some repair to do, you can still use, HTTP to get, some packets coming from the CDN. Okay, we try to add that as small as possible, but we can still do that. What we've been seeing as well is like in ABR, you have like different variants, different profiles. Well, you don't need to put all of them in the multicast too. You can just put like the top one, for instance. The good thing about multicast in an ISP network as well, the bandwidth for that multicast is guaranteed. So you can really guarantee, for instance, that you are going to give to every single viewer 4 Mbps. So the viewers will not need to go to lower profiles. They can stick to the 4 Mbps. Okay? So just like if we zoom a little bit at the agent itself, the one that we have in the home. So if you look at in terms of deployment, one way to do that is to put that on the home gateway. So we have, just us, and we are not the only one doing multicast ABR, but we have like implementation of more than 150 different type of devices. So think about, Wi-Fi router, GPON, cable gateways, all of that can actually support this kind of agent. And if you look inside, it's doing a couple of different things. Third thing is like it's a request router. So it's actually going to intercept the streaming requests coming from the different players in the home. Based on that, it can actually join the multicast, which is requested by the viewer. He receives a multicast, he transforms back the multicast back to unicast, and it's acting like a small cache server, like a small web server that you have in the home. So all the streaming is actually done by this small cache server here. It's not done by a cache server coming from internet, it's done by that cache server here. So a couple of things enabling that. It's now that we can cache here, what's useful is like if you have a lot of different devices in that same network, in that same home, watching the same stream, well, everything is coming from here. You don't need to come back to the network. Okay, so let's imagine in a bar, you have like 10 TVs and everyone watches the same game. Well, you come 10 times here and that guy is coming to get the multicast only once. It can also be on the set-top box. It doesn't have to be on the gateway itself. It can also be on the set-top box. Now with the Wi-Fi 6 gateways, UDP is actually pretty good and pretty stable on Wi-Fi as well. So you can actually put the agent directly on the set-top box. So this works on Roku set-top boxes, on Apple TVs. We have like version of the agent running on all of that. And so in that case, it's even easier, to deploy it. You can put that directly in the application that you run on the set-top boxes. And from the set-top box, using Wi-Fi, you can also stream on all the different devices of the Wi-Fi. So you put the agent on the Apple TV, but if someone else upstairs is watching on the tablet, the stream is also going to come from the Apple TV using Wi-Fi. Okay? So it's not limited to only the main screen. It can be any screen that you have in the home. So multicast ABR, it's a technology which is start to be standardized also. There's like specification coming from DVB in particular. So DVB is pretty strong in Europe, not that much in the US, of course, but it's specification is coming there. And you can see that like the format used in terms of transport can be different. So people are, especially in the US, ATSC is using a lot of norm. Flute has been used in the satellite since a long time. Root also has been pretty popular. So you can use different kind of solution depending of what kind of a solution your vendor is going to develop. Cable Labs used to have some specification since like 2016, so it's also there. SVTA, so if you are familiar with SVTA, so open caching, which is also like a good recommendation for having like CDN caching in the edge, as a new part called open casting, which is giving the capacity for people doing open caching to also provide the multicast resources to content providers. 3GPP, I don't know if you are familiar with EMBMS, which is a capacity to use multicast over mobile network. They start looking at putting multicast ABR also in EMBMS. And IETF is also looking at the multicast transport protocol like MSync to create a standard as well. So while the technology, is still pretty new, we see a lot of standardization and a good adoption rate right now. Multicast ABR is one way to use UDP for streaming. Lately, we've been seeing also a lot of different alternatives. I just highlight two here. One is called Mock. If you're familiar with Quick, it's basically the version to focus on real-time streaming. Probably you see that as a competition sometime, like with WebRTC. Again, like the intent is to focus on low latency, synchronization between the screens. What is interesting is the BBC start looking at putting multicast also over Quick. So it's pretty similar to what we've been achieving with the multicast ABR as well, right? I don't know if you're familiar with SAI, but if you look at Amazon Prime, Amazon is of course doing a lot of HTTP for delivering everything on Prime, especially for the video on demand and stuff like that. But for live event, they try to use as much as possible SAI. So they acquired a company like a few years ago called Net Insight. It's a Swedish company, and we were developing like that proprietary streaming protocol. Same, focusing on low latency on synchronizations. And SAI can also use like what they call fan-out multicast. So basically, they use multicast between different relays inside the network to scale also SAI for some different markets. So if you look in terms of use cases now, why going to multicast ABR? So first of all, I'm going to ask you to put yourself in the shoes of cable operators in the US. You're in the US, you have 500 cable operators. Most of them are still doing a lot of broadcasts. Okay, so proprietary set-top boxes, you have QAM in the network. The problem is like all of these guys, the subs, they ask for streaming solutions. So little by little, they move to IP. If you look at Comcast, you can get Xfinity, stuff like that. So all of these operators, they start to have two headends. They have a traditional headend based on QAM delivery, and they build a new headend based on IP. Okay, well, the problem with that is like, it's a lot of operational issues that you need to deal with. Like you need to run two platforms in parallel. If you use multicast ABR, actually you can have like one single system to deliver your main screen and also like the multi-screen you have on the side. So you can actually stop all of that. You can stop your QAM, you can stop all of your broadcast system. You can replace all the different set-top boxes that you have in the home by, like bring your own device or devices that people can buy in Walmart. And it simplifies, like the operational issues that you have overall. Okay. And again, in terms of capacity planning, same thing. Like whether you run that or you run that, the impact on the network will be the same. Doesn't matter how many people watching the streams, it will be the same from a network perspective. And you have also like the second case, which is what we call the open multicast ABR use case, is the capacity for ISPs to provide multicast capacity to third parties. Okay, so think about DAZN buying capacity of multicast in Italy to deliver content to the subs. Okay, so we can take an example in the US. In the US with the Super Bowl, everyone is very stressed every year for delivering because you have like millions of concurrent stream. So they actually book a lot of capacity from CDN and stuff like that. And fair enough, it worked very, very well. But one alternative to that is like, well, you can actually work with operators. You know, you can work with Charter, you can work with Comcast, whatever, to get multicast capacity from them. And then you don't really care how many subs you have like watching in parallel. You have like one stream for everyone. Okay. And it's really like a win-win situation in the way that like for the people, the third-party content owner, well, good thing about that is like you can guarantee the quality of service. Because again, like the multicast, you tell people like, oh, I'm giving you 15 Mbps. You will have 15 Mbps all the time. So you will not be, you know, sometimes you have congestion in the network. No, the 15 Mbps will stay there for the entire event. And you can optimize your cost as well, because of course you can offload part of your CDN cost to the multicast. And for the ISP, well, for the ISP, of course, multicast ABR is a good solution to deal with their own content, you know, people doing broadcast. But, you know, when DAZN is streaming from internet, it's really like the double-edged sword for the people like that. They need to have like, to put a lot of capacity on their network to deal with this. So they put a lot of investment for not even their own service. And also they need to pay for the transit because all the traffic is coming from internet. So a lot of investment, basically. So actually, if they can propose multicast capacity to third party, well, it's a way for them to limit the investment in terms of infrastructure and in terms of transit. Okay. And of course, you can tell to yourself like, well, guys, if you come to my broadband service, the quality will be better than if you go to my competitor because look, I'm caching the DAZN content, blah, 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 and the quality is better. What we see as well is like, well, if you can start using multicast ABR, it can be an enabler for 4K. Because of course, again, like right now, when you look at the Super Bowl has super good numbers, you know, no problem at all in terms of delivery, there's no buffering or stuff like that. But this, you still like limit yourself to 1080p. Okay. Of course, if you go to 4K, you can try to optimize your codec and stuff like that. But at the end of the day, you need to multiply by 4 your bit rates and the bandwidth that you need, blah, blah, blah. So it's another enabler for multicast ABR. You can actually put 4K on that. Or later on, if you want to do like virtual reality, which needs actually much more bit rate, if you want to do that at scale, well, multicast ABR can be a good way as well. So some feedback that we got in terms of deployment. Typically, what we see on the field is like multicast ABR is a very good way to offload between 85 to 90% of your traffic. We still need to have a little bit of unicast traffic for what I was saying. We need unicast for repairing. So sometimes when like frames are missing or stuff like that, we use HTTP for that. We also use unicast because, you know, like sometime in UDP, you need to join the multicast. It takes time. So we burst in HTTP, the first chunk. So we actually have a very good startup time anyway. Okay, so we need HTTP for that. Okay, and the last thing is, of course, you know, like people start pausing TV, it's not live anymore. So we fade over to the unicast in that case. The agent itself, there's a little bit of buffer. So you can imagine the agent to start keeping the content for a few hours or stuff like that. But you still, you know, you are not going to keep that for 84 hours, right? So 48 hours. So it's just for a couple of hours. So same thing, like, so pay TV is like, this is an operator and Mexico will replace the entire broadcast by multicast ABR. And this is like a case where like an open multicast ABR. So think about the DAZN, for instance, when it's much more event. And same thing, they were able to offload 85% of the traffic using the multicast. So in terms of CDN cost, you reduce your CDN cost by 85%. One thing that I didn't talk about is like in terms of quality of experience. Again, like think about the ABR, right? ABR, the way that like it works is the player is going to decide himself which variant, which bitrate is going to do based on the bandwidth capacity. Is also typically is going to look at the round trip time between the server and the client. Well, in the case of multicast ABR, because the agent in the home is directly, like on the Wi-Fi router, the RTT is very, very small. Because, the bandwidth, again, is guaranteed in the network, that is got very, very good benefits in terms of quality of experience. Okay, so startup time is pretty good. For the latency also is very good because when you do low latency, what you do is like you lower your buffer on the player, you reduce your chunks and stuff like that. So if you can guarantee the network capacity is pretty good. And that's what you doesn't actually experience. They were having a lot of improvement in terms of like failure, in terms of rebuffering. And I think the most important for me is like when you use multicast ABR, where the players stay on the highest profile most of the time. Okay, so you make sure that like people don't move from one variant to the other. So few takeaways about multicast ABR. So multicast ABR, my company Broadpeak, we've been working on that since 2012. We were definitely way ahead of the market, and we were pushing a little bit by ourselves the technology. But OTT was not at scale yet, so people didn't really see why multicast ABR was so critical for them. But since a couple of years, because you have so many OTT services getting sports rights, look at the US. Now you are going to watch the Super Bowl on Tubi. You are going to watch like Monday Night Live on Monday. The game like on the Monday on NFL on Amazon. A lot of OTT services are delivering like live events, and so for ISPs, they are looking at a way to tackle the bandwidth peak for those, right? So the adoption is getting there. On our side, we have a lot of different deployments mainly with tier 1 operators. 85% is a little bit the magic number. That's what we see on the different like deployment that we have, and we see a very good impact on the quality of experience as well. Okay, like if you look at just regular ABR, if you power that by multicast ABR, well, you can also like increase the experience of your viewers. Any questions? Yes.
We've got a question from Mike online.
Okay.
Mike is familiar with Media Over Quick. He says it's designed for fan out, but it's not currently spec'd for true L2 multicast, although MP Quick seems to be a popular research topic.
Yeah.
But here's a question. Is mABR used more within SP networks or at the middle mile to distribute to those last mile networks?
Yeah. So typically the way that we deploy multicast ABR in ISP networks is like the software that we, that I showed at the beginning, what I call the transcaster, is typically sitting in the head end, like centralized, very close to the peering points, because it's getting the content like a player. So it's actually like pulling the content from the CDN or from the origin. So it's pretty much centralized. And we typically just need one server, because think about it, we do that for like one live or for a couple of them. So we don't really need to decentralize the transcaster capacity. So the origination of the multicast is centralized. We deliver the multicast all across the network, and we terminate the multicast in the home, so on the last mile. We've been having discussion with a couple of ISPs to actually terminate the multicast a bit earlier. So like at the edge, very close to the CMTS or stuff like that. But at the end of the day, because it's not so complicated to deliver the agent and to deploy the agent in the home, now that we can do it also on Android TV, on Apple TV, we actually terminate the multicast in the home. Yeah.
Like when it's switching between unicast and
Yeah.
multicast, is there ever any client affected kind of behavior?
Yeah.
buffering or?
So because the switch is actually always done by the receiver, so for the client perspective, is always receiving HTTP, and is following his playlist. So way you do it in HLSA and Dash. So the glitch is not seen by the player. It's all the logic. It's really done by the receiver, and that the receiver is in charge of switching back and forth between multicast and unicast. Is the one responsible of that.
So how much latency does it have?
So actually, in terms of latency, it doesn't add any latency. There's no additional. We don't process more the video. We don't add any buffer on the player side. We don't touch the buffer itself. So there's no additional latency. Actually, what we see is like when people start implementing, they realize that they can actually reduce the latency because again, they guarantee the network capacity.
But certainly has to be some additional, under good network conditions, obviously. There has to be some additional latency added because you add the additional processing of unicast after you receive the multicast signal.
Yeah. So this is not really like video processing. It's really like because we just remove like a header and we replace by another one. The process it's very, very minimal. And again, like think about it, like we still keep HTTP to start the stream. So the first fragments are coming from HTTP. We don't add any latency there. We just catch up with as soon as we get the multicast inside the receiver. So in terms of latency, there's no addition of latency at all.
Then what do you attribute the low adoption rate?
So I think there's a couple of different reasons for that. First of all, like a lot of ISP got a bad taste from multicast. So especially telcos, they used to do a lot of multicast when they start doing video services, and so they don't really want to come back to that. That being said, I think there's the balance between the effort and the benefits are super high. So while you put a little bit of effort for that, you have like very high benefits in terms of investment. So that's one. There's like kind of like misconception about like how multicast is complicated to deploy in networks. I think that's number one. I think like for some people, they still do believe that like live is not that dimensioning yet, because they say like, well, I need to dimension my network for Netflix anyway. A lot of people, 50 to 60% of traffic is Netflix. When you add YouTube is 80%, and so I need to dimension for that. And last October, Netflix started doing live events, and everyone will like start panicking, And you see like the issue like Netflix got like most of we got like customer feedback on like ISPs like really struggle with the delivery. So there's also like some it's coming because of like the usage are moving as well. So. Yeah, but well, one slow adoption, like think about it. Like most of the time, if you look at ISPs, yes, in the US you have 500 ISPs, but if you work with Charter and Comcast, you already work with 80% of Americans, right? In France, like you have 3 operators. So for us, we already deploy with like 30 to 40 ISPs. So while the number may look low in terms of people, in terms of subs and viewers, it's still a good numbers. So it's still like the critical mass is getting achieved. And that's the reason actually DAZN is working with us, is because when they work with us in Italy or when they work with us in Spain, they touch a big enough footprint. So, like it's make it relevant for them to implement the technology. And I think the challenge for us is really like to make multicast mABR easy to use for people like DAZN or for anyone doing live OTT. Okay, right now is still also like there's complexity to get access to multicast from operators. It's not like plug and play. You need to talk with the operators. It's still a complex process.
Thanks to Mathias.
Yeah, thank you. Thank you.
That's the last one here. If you want to just pass.
So you have like, it's magnetic.
Oh, there you go.
Yeah, you go.
Well, it's not sure.
That's where the animation was really good.
Do you want me to airdrop it? Or you got it?
Oh, yeah. I like the pictures.
Yeah.
I get your point there.
Yeah.
I'm disappointed.
I passed a lot of time on it.
Shift the down arrow. And...
Oh, okay. Sounds good. All right.
All right, last one. People can feel free to grab more drinks and pizza.
Should I start now? All right.
Go for it.
Good. Okay. All right. So today, compressing video with neural networks. This is kind of a little passion project of mine. Past couple months, and still kind of early. So now it's this presentation is going to be a little more theoretical, kind of seeing where the market's at right now, what opportunities we can get into. So I'll start with a little bit about myself. Seems like up is down. Oh, there we go. Okay. Yeah, this is kind of going into a little new era of video. So a neural video codec is basically a video codec that leverages neural networks rather than traditional, H.264, HEVC, and all those kind of traditional codecs. And the main kind of goal here is for better compression while improving visual quality at the same time. So it's kind of a 2-for-1, kind of ordeal. So, but the main problem here is kind of overcoming the challenges that comes with hardware. Not every device has NPUs and GPUs, so it's still kind of early. But once we're at a point where most devices are able to play these codecs, we need to take advantage of that, basically. So a little bit about myself. My name is Ahmad Sandid. I started off way back when, before I even knew how to write a line of code. I started in filmmaking and graphic design. So a lot of video there. When I started coding, I started in fintech, making a lot of B2B SaaS, trying to make ML models very consumable to the average person. So later on, I worked on the first end-to-end software-based background screening service. So that kind of leveraged a little computer vision, try to get people to verify with their IDs. And then afterwards, I went full into streaming services. I worked at Disney, and they have a lot of different products. Disney Plus, Hulu, ESPN Plus. There's a lot of variety of the problems that they need to solve as it relates to video. And I took a lot of what I learned there to my current company, Crunchroll, which, usually when I ask people if they know Crunchroll, they tell me, they ask if it's a sushi, which makes me hungry, but I have to answer. It's a streaming service similar to Netflix, but just for anime. I work on the transcoding and packaging team there, if this wants to work. Basically, to kind of break it down, we do transcoding and packaging. So transcoding, of course, at its essence, is converting video and audio files from one file to another. Usually our work is on the infra side of the video pipelines, but we basically kind of try to get device compatibility, bandwidth, and all that. And then we also do packaging. So when you go onto Disney Plus and play a video, you don't download the whole file. It's video streaming, so you get chunks of video your way. There's a little nice picture of me getting a 50 gigabyte mezzanine, and that's what I have to deal with every day. Try to get that down, compress it, make it playable for anyone. When we think about video and internet, every year more people get online, and also more people move from cable to internet streaming services. So if you look here, it's kind of an upward trajectory, but it's only going to go higher. And the demands for 4K and 8K is going to come. 8K, needs some time, but 4K is definitely kind of trying to get into demand right now. So main problem here is compression. And what is it? It's pretty simple, right? At its core, it's representing information with fewer bits. But as it relates to video, we want to reduce the file size, reduce bandwidth, while still maintaining QoE, which is kind of, you can pick one or the other, and but we want everything, right? And when it comes to compression, there's lossy and lossless codecs. Lossy, of course, you lose data. It is a lot more efficient. You lower bandwidth. For lossless, you have the exact one-to-one replica, or it should be at least, when you compress and then decompress. So here's a little couple examples for lossless. Pam's looking at this and she's saying, the raw video versus the decoded video. So the raw video is what you compressed, and then decoded is after you decompress. And it should be the same. Lossy is, it's kind of similar. There's some stuff, lost in translation. So this is a great example of lossy codecs. This is an actual screenshot of a video of Sonic that I was watching on x.com, the everything app. And it's also the lossy app. So it was very high quality gameplay. But yeah, before we get into neural networks, we should know where are we at right now. How do we currently compress? So the main problem is here we have a 4K video. It's if you wanted to stream that for 1 hour, it'd be 2,700 gigabytes. So you need like 6,000 megabits per second. I don't have that kind of traffic. The average person usually has like 80 megabits. So big problem there. We need to compress it. From a high level, we have an encoder and a decoder. We start off. I'm not sure if y'all are familiar with the DCT, discrete cosine transform. That's the biggest first step. We start with that. We quantize, and then we use the entropy encoder, and then we have the compressed image data. And later, we're basically undoing what we did here. So we decode the entropy, and then we dequantize, and then we do inverse DCT. So transform coding is kind of looking at video how a human looks at it. If you saw a space here, like a white blob, you're not going to say white, 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 and keep repeating that like a for loop. We're not robots. We'd probably refer to it as, oh, this section, we have a little white section here, we have a little red there. And what it'll do is it'll take those pixels and represent them as frequencies. So instead of repeating that same information, it'll just say, 4 beige pixels there. So it leads us to afterwards to quantize. And quantization, well, I think we'll get into it a bit. A big part of traditional codecs right now is motion estimation. It's kind of where it's weakest because of the fact that it has to, if you're doing 2-pass, you have to get, iframes and p-frames. And what you're trying to do is saying that, you don't want redundant data. That's the biggest kind of thing with compression. So instead of just repeating the same pixels over and over, you can pick a block and say that it's moving. And you can save a lot of data there. Quantization is my favorite little, trick when it comes to compression. What you're saying is, if you have like since we represent the colors as frequencies, we can also minimize things. So instead of saying teal, turquoise, and all of different variations of green, you could just say green. But the main, trade-off is if you just say green, turquoise is pretty different than, it has a little blue in there. So you're losing a lot of data. So the more you quantize, the smaller the file size, but you also lose a lot of data. And this is a great example. This is a bad quantization. But if we see here, it's summarizing the pixels. So that's why you have these like different like sections here, where it's saying this group is kind of alike, so we're just going to group them together, and that's just gray. So we're going to ignore whatever values they actually are. The limitations, these are handcrafted algorithms. The performance benefits from one to another is kind of decreasing. We're kind of almost reaching kind of a peak. They're prone to introducing artifacts at lower bit rates. It can't recover. It can't fill in pixels that it doesn't already know. So it kind of needs all the information. They're pretty slow moving. Like AV1 has taken a lot of years to get adopted. In the same way, it doesn't leverage what we already know about video when it comes to the actual like codec decoding. It can only be programmed to do something. But it won't, use context from previous videos that you can do with neural networks. So this is a great example of pixel soup. So one of the things when you think about like quantization and artifacting, when it's a high motion scene, we can't reuse a lot of the motion, and because you need more data to represent that. So a lot of times when you get a really high emotion video on like a live stream, it starts looking pretty bad. You can't see Patrick, hidden SpongeBob here. So we segue into neural networks. There's a nice kind of little meme here of me throwing out 20 years of video research and advancements, because that's exactly what we're going to do here. Pretty much everything that we do, previously that I was showing, we kind of throw it out the way, and the the encoder and the decoder is going to be the neural network. So we're kind of plugging and playing here. And when we talk about neural networks, from a high level, we have these little neurons here, and we have an input, and we also have an output. So the input is going to be raw pixels, and the output is going to be some decompressed version that later on that we can test against. We have this idea of neurons, and neurons make predictions. So let's say for a certain pixel, it's going to predict a certain value. And what we do is we group them into layers so that we can have the different neurons communicate with other neurons, and they can make higher level inferences. So if we look at like, there's a big principle of you can have the neural network make a reason of a photo because it's looking at different sections. So it starts off with however many pixels that frame was, and then it starts with this really granular point. And as we get higher up in our layers, we're going to make out certain parts. This is how it makes sense of, let's say, the number 9 versus 8, because it looks at the high sections and it says, oh, I have a line here and I have a circle there. Whereas when it inputted, it just had a bunch of different pixels. So it's trying to make these higher level assertions, and it allows you to kind of make sense of what's in the video. Is that a tennis ball? Is it a basketball, for example? But the biggest problem here is, as we've seen before, there's a lot of connections. And it's really expensive to train these neural networks. And we also don't want to overfit on our data. We don't want our training data to conflict with what we're actually decoding. Let's say if we have a new show or a live stream, you don't want the existing data to impact the actual output in a meaningful way. So when we look at training, the biggest part here is something called loss. So we calculate loss. What loss is basically checking ourselves during the training process. So what we do is we have a test video, and we have a output that like an actual output that it should decompress to. And we compare, we throw the video at the neural network, and we'll just let it predict. And then we're gonna say that, hey, you were way off the mark. Try that again, buddy. And so it's gonna go again on that neural, that neuron's gonna predict again at a certain weight. And then it's gonna say, okay, how about this? And you're like, okay, a little closer, but keep going. And it'll keep doing that over and over. And that's kind of the main goal of something called gradient descent. You want to minimize loss. You want to get to a point where it'll keep diffing. And at some point, we get to a point where the weights are really accurate, and it's actually predicting the right way. So there's also a lot of techniques that we're using here, like backward propagation, forward propagation, where we're each of these neurons could have, we can use something called like an MLP, where we have multiple neurons, and it can keep looping over those neurons. So yeah, AI, neural video codecs, they have been worked on before. I'm not the first one to do this. So we have to be familiar with their game. This is kind of a good, I think, seed starter. The reason why this is SoundStream is a neural audio codec, but the reason why I bring this up is because a lot of papers that came out afterwards for video codecs, took similar ideas in the way that they represent denoising, the different neural networks that they use, to represent higher level. Like if we think about voices are very specific to a person, and it's very granular data. So if you want to recreate it, it still has to be granular. You have to be like close to lossless to get someone's like accent and audio right. So what they do kind of superseded a lot of the video stuff, because if we think about like the top models that came out initially, speech to text, text to speech, and all those models. That's kind of what started it. And later on, then video kind of came in. So this is kind of the first, I think, pretty close model at using full AI and full neural networks. It's made by a cellular carrier called Orange, if you're familiar with it. Not really in the US too much, but they wanted to solve the problem of using to minimize a lot of their video transfer. So what they wanted to do, what they used is two autoencoders, MNet and CNet. And these are kind of pre-trained neural networks. And basically, a lot of their paper focuses on motion, which is where usually codecs kind of lack in. Why? Because if you can make sense of the objects in the video, you can also make sense of motion. And because of that, you can represent that same motion in lower amounts of data, because not only is it making inferences on large parts of the video, like saying, hey, there's a ball here. In the same sense, it doesn't have to recreate that ball every frame. It could say this ball moved from left to right, for example. So from a high level, it can kind of represent motion a lot better. And it also, since you have the context of the entire video in that model has context of many videos from all the weights that it made. It understands the entire video. Like, let's say with speech, it knows when I say something, my mouth is going to close again. So for example, there, if it really knows speech very well, it can represent speech in a much smaller way. Grace is a really cool model because they focus on recovery, making really resilient codecs. So if you have a spotty connection, or if you're doing video transfer in a very high traffic location, or even a remote area like Antarctica, what it's saying is, since we are using neural networks anyway, we could use generation to fill in any missing data. So what it wanted to make and set out to do is to make a video codec that you can miss some parts in the data, and you can really make the data transfer and the packets super small, because it can recreate and fill in gaps in the data. So what it'll do is, if it doesn't have a piece of like a certain video frame, what it'll do is it'll just mark them all as 0. So if you think about a video frame as like a tensor or like a matrix, if it's certain parts it doesn't know it, it'll just infer from the things around it, which is very similar to super resolution, but it's kind of different because what they do is they compensate with motion. And the encoder, like the neural networks that they use, is very different than what super resolution neural networks will be used for. So if we think about NVIDIA, they have DLSS. It's very different than DLSS, but it's the same idea, which is if I can't make the frame, I can, as long as I have some parts of it, I can kind of recreate the rest, or fill it in. So you can kind of upscale frame rate, for example, kind of fill in those frames. The main problem with this paper, in my opinion, was compute, which is on a phone. It's that's kind of the main trade-off here. Deep Render is a really interesting company that I've been looking at, because they're the first company that just focuses in AI video compression only. They're a London-based startup, and they're one of the first. A lot of the things that I've shown before is mainly like white papers. What they work on, they actually have a FFmpeg and VLC plugin that you can try out. I'm not sure if they released it publicly this year yet, but they are planning to roll out with an actual streaming service with actual production traffic sometime next year. Now, we don't have too much information on how the model was actually created. From what they mentioned and how it's being used, we can kind of infer a lot of things from what they've been saying. And from a high level, they're not giving us their recipe, but they are saying from a high level they're doing similar to what the other models I've showed are doing, where they use a neural encoder, so you can have low dimensional representation of that same data. And for decoding, you reconstruct the image, and you can save a lot of cost and network from that. And of course, motion is a huge theme here as well. So a lot of these codecs care a lot about motion. What about transformers? The reason why I bring up transformers here is because they really revolutionized all the models that we see today. So if you think about ChatGPT, DeepSeek, Claude, Copilot Llama, even the image generation, so Midjourney, as well as or the image, video generation. So for Sora, we wouldn't have these if it weren't for transformers. And what transformers are is they use something called self-attention. So every, let's say if we think about an LLM where it's like generating text, each one of those kind of 4-character pieces of that output has the context of other neurons. So if we could search, I could show this on the next slide. Traditionally, video codecs will use something called RNNs, which it maps the neurons together. They'll also sometimes, so let's say Grace will use like a CNN, which would have a lot of context. It also costs a lot more to train. Self-attention is really powerful because you have local, so similar pieces of data are really close to each other. So when you go to the next piece, when it's just generating something, it has the attention of everything around it. It's almost like the best way to encode information. So if you think about, there's some really small LLMs. Let's say you can have a 1 gigabyte LLM I can run on my phone, and it'll have basic information about all of the internet. So it's almost like having the internet in your phone. In the same way, you want like a whole live stream. Imagine if we use that same application, you could save a lot in encoding and decoding. If we think about, we can also integrate video generation if we used transformers. And the nice thing is if you connect your encoding and decoding with a separate generation model, you can insert generation while decoding. So we think about, it's very similar to like client-side ad insertion versus like server-side. In that sense, you're not including certain video generation during encoding. On the user side, if they, let's say, really like a certain color profile, you can add generation where during decode, there's a last step where we add another layer and we insert kind of our own preferences, our own weights that could be specific to a user. So yeah, that's transformers. They're pretty neat. The pros of neural codecs from what we've seen so far, this is a good graph from DeepRender, where they were comparing some benchmarks in terms of how efficient it can be compared to AV1, HEVC, AVC. I think it's still a little early to make these. I think later on, some better benchmarks need to be made when it comes to AI video codecs, because what it's not being shown here is a lot of the stuff that I think I'll get into the next slide, which is some of the cons. But the good part of neural codecs is that you have semantic understanding of your content. It knows what a ball is. It knows what a car is. So it uses all information from all its training data. So it doesn't have to be given. It doesn't have to be taught a lot. It's a very smart codec. A lot of the use cases, of course, streaming services. As I work on a lot of streaming services, so I'm biased here. But also for video conferencing, if someone's talking and you like disconnect, let's say from the VPN or something, you have like those 5 seconds of you're just looking at like a blank face and then nothing's happening, but you're hearing their audio. A neural codec could make sense, especially if we use something like Grace. It's very resilient, so it can kind of infer from their speech what they were saying. For surveillance, so if we think about, let's say here in Chicago, we had a lot of cameras that are like around in the streets. So if you wanted to make more efficient transfer of that, maybe enhancing, upscaling based off of what it's seeing to maybe alert authorities, for example, you could use neural codecs and they might be a little more efficient. For VR and AR, let's say if it understands what it used to see. So let's say if you're looking one way, you turn back the other. It has to reconstruct all the pixels and render. Let's say what's behind you again. If it remember what it saw before, it can kind of recreate that while it's generating frames, which is similar to what a lot of, let's say, DLSS or super resolution models already do. The main challenges are going to be hardware. That's the biggest thing. We're a little behind here, on the hardware side, but our neural video codecs are pretty early. in the game when we think about what's available. So let's say iPhones have is kind of relying on NPUs, which are neural processing units, and a lot of devices. Let's say a MacBook, and every iPhone since the iPhone 8. Galaxies, they have them now. They're kind of advertising. Let's say Galaxy AI, Google Pixel's doing the same thing. But you have so many devices that don't have these yet. And the reason why we wanted neural video codecs is so that people in remote areas or people that are just getting access to the internet for the first time, can use and stream at 4K. That's kind of the goal, the North Star. But if they don't have the compute for it, that's kind of the biggest trade-off there. It is getting better since LLMs have gotten so popular. Most devices are being equipped to handle that anyway, so we can use those same advancements in the same way. LLMs like ChatGPT are becoming almost like an integral service for a lot of people. We can, since those devices are going to have that, we might as well, be able to capitalize on that as well. I think the biggest problem from what I've seen is smart TVs. I think laptops can run a lot of local models pretty easily, but smart TVs, I think they can barely, open a web page or, like move. If you move a button, like just showing like moving in animation, it has a lot of problems with that. So a lot to be done. I think dongles like Roku and Chromecast are looking to add NPUs at some point in the future. Especially when we think about AV1 is already hardware intensive, and that doesn't have any GPU acceleration for a lot of these dongles. Later on, if they add NPUs to support AV1, we could use those same, neural processing units for our model. And then also training data dependence. We don't want our training data. We want a lot of training data such that our training data doesn't compromise the actual stream. The main ethical concern is, a lot of these codecs don't mention video generation. That's one of the things that I wanted to add. The main problem is there's some people looking into adding video generation for, let's say, ad insertions. This can be good. So let's say at Hulu, one of the problems that we had where no one wants to pay for the paid version with ads. They don't want to see ads. They want free, but they don't, they want the world, right? They want ads, they don't want ads, and they don't want to pay a subscription. So one of the things that people are looking at is maybe saying, okay, you can watch the video, but for a certain amount of time, you're going to see ads. Let's say if someone picks up a can, it's going to show Coke on it. If someone's, let's say, has a car, it's going to be a certain brand. You can patch that in the video generation. So as you're decoding, let's say certain pixels, once it realizes like, oh, this is a car, it can point to a section and then add video generation. In the same way, there's a lot of models that does video to video. We would be doing that during our decode step. So that's kind of the main. We don't want to compromise the artistic integrity. There's some degree of error because it is lossy. So if someone is like, it's a really integral part of the story that someone is like lifting up 2 fingers, but since we're doing generation, maybe their device is really bad and it thinks that, oh, it was a full hand. It's kind of might hurt the story, right? So we want to make sure that we err on the side of full entry. Like when we think about generation, I really want it to be a minimal add-on, not something that kind of takes over neural codecs. So yeah, that's who I am. Yeah, modsandid.com. I'm on X, and yeah, I'll be posting a lot of updates as I kind of roll things out, get things in production. Having people have people try it out. I need a lot of GPUs, so if y'all have any, feel free to donate. I need so many GPUs. I also need hard drives for all this video. I think the average training data set was around like 2-3 terabytes per data set. So yeah, compute is needed. Yeah, that's video codecs.
Any questions?
We got a question from Rebecca.
Awesome.
All right. Is neural network transcoding still expensive once models are trained? Could it eventually help restore low-quality digital archives that aren't currently fit for distribution?
Low-quality digital archive. Yeah, this is actually a great point. So, of course, the training of the model requires some crazy GPUs. The actual model is a very small thing. Like we've seen, like let's say deep render. Their model sizes are around 150 megabytes, which isn't too bad. So let's say you download an app at some point. It's like, oh, do you want to use, AI acceleration? You could just, hit yes. It'll download 150 megabyte model. But the actual training takes way more GPUs for that. When we think about restoration, so if we look at like one of my favorite movies is called The Bicycle Thief. It's like an Italian movie from the 40s. What if we could colorize that real time? Because it can make sense of things. There's already people that do color restoration, let's say for manga, which is like black and white comics, right? So we could use that same thing there.
Rebecca also says the world could finally see Flo's Diner again.
Exactly.
All right, question from Mike online too. How might AI codecs change the IPR and licensing landscape? Do you think that will be better or worse than the current system of patent pools?
I think it's going to be a lot better because I think the only path forward is to use open source models. Like any model I'm creating, I plan for it to be open source. If we look at a lot of the models, like let's say DeepSeek, because of how good the open source models are, the reason for licensing and closed source models like Claude or ChatGPT, where you have no idea what's going on inside and you're not entitled to know any of that, it's really a big differentiator. And I think if we're trusting these decoders to be on any machine, I'd also want it to be open source and a very good license. And it seems like a lot of these papers are really telling everybody their whole recipe. So because of that, I think it'll be way better than, let's say, H.264, HEVC, and a lot of these other codecs where the licensing is really bad. I haven't seen any neural codecs mention licensing other than the fact that, hey, we don't have that. So might be a little plus there. So anything else?
So where does the funding come from then? If a lot of the research behind these codexes, especially like HEVC and so on, it came from bigger organizations, right?
Yeah.
That invested some of their energy and obviously a lot of energy into IP and protecting their IP and so on. So, what is the difference between the neural network codexes and?
Yeah, it seems like a lot of people that are pouring into research they're not doing it's not like HEVC, for example, where you have a lot of companies partnering together. With these, it seems like a company will roll out something. So Microsoft, Qualcomm, for example, they both release their own neural codecs, and it's just them. So they're funding their own research. In the same way, Google may release Gemma, which is like a local source model. They'd also be releasing these. Let's say DeepRender is all venture backed. So that's how they're getting funding to train everything. And they already have deals with streaming services, for example. And I'm assuming that's where they're getting the venture interest. And that's allowing them to pay for all the things that train. So for me, my training is spending a lot of my electricity bill. But later on, as I get closer and really, put a team around it and everything, I'm sure we'll have a lot more funding, a lot more compute to make these really efficient. Yeah.
Thanks so much.
Yeah. All right. Awesome.
Appreciate everyone joining online. Yeah.
Thanks, everybody.
Thank you.